section. Um, yeah, so I think the thing about this question that I keep sometimes kind of getting confused with is just, I guess if we could quickly just go from balancing an equation, because sometimes I keep missing this. I don't know how they got to this thing. Because like I knew how to do it, but the fact that I couldn't create the balanced equation just honestly messed me up.
Anything in the passage about it?
As far as I can tell, not really. Let me see, hold up. Basically it says that I think the biggest thing here, like sodium, lime, and silica gel were added to the chambers to eliminate water and carbon dioxide. And then the question just says calcium hydroxide is a primary component of soda lime used in the experimental chamber. It reacts with carbon dioxide stoichiometrically to produce a white precipitate. If 2 moles of soda lime completely react with excess carbon dioxide, how much precipitate will be produced?
Yeah.
Um,
So calcium hydro like are you able to like read that it says calcium hydroxide and write down what the um chemical thing is for it?
yeah, so I got to this part. Like I remember I wrote this and then I wrote white precipitate, but I didn't realize that this would react to form this molecule here. But I'm having trouble for some reason, like figuring out how they got calcium CO3. I tried to check and it was like apparently they used like the bicarbonate buffer system and created like HCO3 or something. I don't know, it just got a little complicated.
Okay.
But I just don't know how they got CaCO3.
Okay. Let's see. So, okay, we got CaOH2 plus CO2. We would get, so they're saying a white precipitate. Now, the, you've seen hydroxide ions, you've seen carbon dioxide and stuff, but um our precipitate should include calcium at the very least, right?
Okay.
Right? Like this can also perhaps fall under polyatomic ions and solubility kind of rules.
Okay.
So, okay, so let's see. Um, okay, so I see in the passage they say this soda lime and silica gel were added to the chambers to eliminate H2O and CO2. Um, well, okay. So let's see. Um, this could be perhaps outside knowledge, but if we're being told that 2 moles of calcium hydroxide reacts with excess CO2, the calcium hydroxide is going to be that limiting reagent. Um, and yeah, if we see this reaction, like, and you're unsure of, I guess, how to move forward, we can think about it um like this, like so calcium carbonate is a solid. Or let me see if I was trying to find like if I can I was trying to see if I could find solubility rules to be able to answer this, but I know that when you have calcium, like when you have a 2+ ion,
Mhm.
like a lot of it will be insoluble. Um, all right, let me see what they wrote down there, like beneath in the explanation. Like, I mean, yeah, like way down.
Oh, here? Oh,
Yeah. So we're talking about,
didn't seem very helpful when I read it, but I don't know.
um, all right, let's go back up. Okay. Calcium hydroxide. So I think there's like a rule that like alkali metals in the presence of water, I think, produce hydroxides, I think, or something like
Oh
that.
yeah, I remember that was one of those Jack Weston things that we went over.
Mhm. Yeah.
Forgot about that rule. Okay.
And if you remember, like, both like hydronium ion and hydroxide ion can come from like the autoionization of water,
Ionization of water. Okay.
right? So, hydroxide, you can link that in your head with water.
Okay. Hydroxide with water. Okay.
Uh-huh.
Oh, yeah. So I was trying to find my Apple Pencil. Okay. Yeah. Hydroxides react with water.
What,
Okay.
uh,
So if that's the case, if we, I guess if that's the rule, if we know that calcium
what, what,
isn't
what did you say the rule was? What was the thing that you wrote?
what I wrote on my iPad.
Yeah.
I mean, I was gonna write the rule right now, but I just wrote like hydroxide, uh, to just quickly, just like to think of water as well, typically.
So what it really is alkali metals, right?
Hmm.
Group two,
Group two. Yep.
they react with water, creating um like a metal hydroxide.
Right.
And typically it can also release like hydrogen gas. But yeah, that's typically what we see happen. So here though, they're reacting it with CO2. So we still want to see like a water kind of produced.
Hmm.
And because if the so if like calcium, whatever, solid plus water yields the calcium hydroxide
Hmm.
plus H2 gas. That's the typical uh reaction here. So for us, since we are starting with the calcium hydroxide as a reactant, and we are not using hydrogen gas as a reactant, but instead we're using CO2
Okay.
as a reactant, then we should still get H2O as a product. It's just that this part over here, instead of it just being calcium solid, it'll be um, something related to the CO2. So that's where the calcium carbonate would be. And that's perhaps one way of maybe trying to like figure it out. Um, but for me, like I have a little bit of outside knowledge here because I know like like a coral reef,
Hmm.
like what is it?
Just an area with all little corals, I guess. Little,
Uh-huh.
yeah.
So so yeah, like that type of sea life there um produces a lot of calcium. So yeah, produces a lot of calcium carbonate. That's what coral reefs
Gotcha.
are predominantly made of.
Okay.
So I kind of had, some outside knowledge there. But but yeah, so far I don't see anything else here that can really help us figure that out. But I think what we might be able to do is, if we know that, so let's say that this is so we at least are able to know the reactants, right? Right. Um, so we could say that you can have some type of calcium, like this, the OH is going to be contributing to creating water. That's going to be a thing.
Mm,
And so the leftover is calcium and CO2, right? And,
yeah.
if you think about it kind of like this, like the H2 gas is just the water without its oxygen. And that's kind of what happens because here we have um, CO2 with two oxygens and then CO3 with an additional oxygen. So that could be like this, except that instead of making the H2 gas and releasing the oxygen that way, you can release it with the H2O. But yeah, I would say that this one is relatively hard to suss out in terms of like what the products would be. Um, so yeah, so that could be difficult. Um, but
Could we just say that since if it reacts with hydroxide, we know it creates a water molecule. So at the end of the day, we still need to balance the equation. So there still need to be like three oxygens and a carbon there, right? Could we go that route or no?
it's already balanced, I think, right? You have one
I
cal.
mean, like, let's say if you had calcium here, but I mean, you still needed to fill this out, right? So like that's what I was saying.
Yeah, yeah, yeah. Yeah, so like let's say that you just have the calcium part down, and if you know that you're gonna get H2O, that can come
Mhm.
like perhaps like, an OH group here that takes an oxygen from CO2 perhaps to get, oh wait, sorry, OH2. So we have two OH minus um ions. So that's where the two H's come in. And and then you'll have uh two oxygens, but you only need one oxygen for the H2O. So one of the other oxygens can just be like donated to the CO2 to make the CO3 minus, and then that can fit in for calcium.
Okay.
Mhm.
It's a weird one. I tried to do the little double replacement thing, but I'm like, that doesn't make any sense.
Uh-huh.
But okay. But that makes more sense though. Okay. Next one. Wait two. Okay.
Okay, so
Yeah, we can do this. Yeah, this was
I
very confusing.
have to read this. So
Yeah, I guess we can go to the passive follow.
eukaryotic cells require folate vitamins as cofactors in the biosynthesis of thymidine, purines, and certain amino acids. Antifolates are thus able to slow the rate of DNA replication in mammalian cells. This effect is especially pronounced in rapidly proliferating cancer cells. Oh, interesting. Okay, so the folate vitamin as a cofactor can help make uh, amino acids and what else?
Folate acid makes amino acids and I guess the nucleotides.
Yeah, right. The thymidine, purines. So good, 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 good. Okay, and then if antifolates slow the rate of DNA replication, we could say folate,
Increases.
yeah, can be proportional to the rate of DNA replication.
Okay.
And now, the last thing they say, like especially pronounced in rapidly proliferating cancer cells, I'm gonna make a guess that they're probably gonna be like, so we're gonna try to use this, to cure cancer. But let's see. Folate is transported into cells by utilizing a reduced folate carrier, RFC, and folate receptor alpha, FR alpha. So these are so the carrier carries the folate, and
Mm-hmm.
receptor is, well, it's a receptor, right? Uh,
Mm-hmm.
this is kind of like how, for instance, like fats or lipids in our blood, since they can't be soluble in the blood,
Mm-hmm.
they need like a carrier.
Right.
Okay. So now FR alpha displays relatively high affinity for folic acid, relatively low affinity for the tetrahydrofolate 5-MTHF, and very low affinity for MTX, an anti-tumor agent. Okay. Um, so that kind of makes sense because they were saying like, folates cause high rate of DNA replication, this
Mm-hmm.
cancer cells. So it would make sense that an anti-tumor agent would not very much bind. Sorry. So let's see. Okay, researchers hypothesized that antifolate resistance develops from the overexpression of these receptors by cancer cells. Okay, so I could say that um, FR. alpha, you could say like FR alpha is also proportional to this DNA replication rate, and F
Okay.
and FR alpha, I could also say can confer. I'm going to say AF to mean antifolate resistance, which I guess I don't have to write because it's just going to be the opposite of the folate thing. But yeah, if you have um an overexpression of, I have a better idea, so I'm going to do this. Oops. Um, the alpha proportional to antifolate resistance, and then I would say antifolate resistance is going to be, or rather, yeah. So whatever, I'll just leave it like that. So, um, okay. A study was initiated in order to investigate this possible role of FR alpha in antifolate resistance. Okay. Three new cell lines were established by introducing foreign nucleic acid from FR alpha or FRA, cDNA, or RFC cDNA into osteosarcoma cells, osteo, that did not contain FRA. This resulted in a stable FR alpha. So I'm like, is FRA seems to be different from FR alpha, right? Why would they say FRA? Anyway, this resulted
Yeah.
in a stable FR alpha expressing cell line, osteo FR alpha, and stable RFC overexpressing cell line, osteo RFC. Um, Not sure what RFC stands for. Um,
I think there's a reduced carrier.
oh yeah, good job. Um, got it. Okay. So let's see.
No, yeah, this was really complicated.
So so osteo FR alpha is just regular expression of it. RFC will overexpress it. Um, okay, and then MTX was labeled with tritium, and 3H MTX uptake by each of the new cell lines was measured at different HMTX concentrations, figure 1. Uptake rates less than. Okay, so we have these different affinities for these things, and so when we do this experiment, we have um the osteo condition, which is
Hmm.
without FRA, and then osteo FR alpha obviously has the FR alpha, and then the RFC overexpressing one they have here. Um, and that MTX, which is an anti-tumor agent, was labeled with tritium. Do you know what tritium is?
Yeah, it's like an isotope for hydrogen, right?
Uh-huh. So You see this?
Yep.
So that's my cat, and around her neck, it's kind of you could see like yeah,
Yeah, I see it now.
you can see how it's like lit up.
Around her neck.
Yeah.
It's a little hard.
Here, I'm gonna turn off the see it now.
Around the neck? Where?
There.
Oh, yeah, 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 on the neck. Yeah, yeah, I see it. I see it. I see it there. Yeah.
Oops.
Hmm.
That's tritium.
Oh,
And I always tell people that because the thing is, like, I learn things from everything, like including movies. So, like the Tobey Maguire Spider-Man movies.
oh yeah, love him.
So the second one,
Hmm.
they with Dr. Octopus, he
Yeah.
does the experiment with cold fusion,
Hmm.
right in the beginning. Um, and he makes that big like sun thing.
Yeah.
So he starts off by saying this is precious tritium. That there's only like a few pounds of this, like, on the planet. And he's like, thank you, to Harry Osborne from Oscorp Industries. And then he's like, happy to pay the bills, Otto. So that's tritium. So basically what's the significance of this? What does a regular hydrogen atom include?
Just a proton and a neutron.
Um,
Two more, one
what's
proton.
uh
What's that?
what's the mass?
So it's one, right? Yeah, no, I think it's just one proton, right? I think.
Yep. One proton, one electron, no neutrons, right?
Hmm. Okay.
Now, if you have it with one neutron, we can then call it, I mean, it'll still be H, of course, but it'll have a mass of two now, and we call that deuterium.
Right.
And then if you have two neutrons, that'll be called tritium,
Hmm.
right? And, you know, tritium is inherently radioactive, like it shoots out beta rays. And um, if you cover it with like a phosphorus coating, that it can light up when the beta rays hit it. And so it's used for like exit signs, the sights on like a gun, um, and the things that I use for my the necklace of my cat because it basically glows forever, essentially. And
Oh,
yeah, and it's like I think it's like $30,000 a gram, so it's super rare.
jeez.
I mean, it's a lot less than a gram, like what I have for my cat, but I it's pretty cool because like I'm pretty sure she's the only cat that actually has that. I had to get it from this guy in Taiwan, actually. It's a product of like a nuclear reactor, and the reason that Dr. Octopus used it was if you take so like in our sun, we make like all the elements that you see around you are made from suns, from stars by
Yep.
fusing things. So in our star, we have hydrogen being fused into helium.
Hmm.
You can do that easily with tritium because you just add a regular hydrogen to it, and then you would get your helium because you have that mass of four.
Oh,
Yep. So yeah, so that's what they mean by tritium. They're going to use it oftentimes to label something, isotopic labeling. So they labeled the anti-tumor agent MTX, and it
mm.
seems like they threw that in and then they measured the uptake of that anti-tumor agent, the MTX, uh,
Yep.
for each of these cell lines, right?
Mm.
And it should make it should make sense that we should see like perhaps like before I look at the graph or whatever that the FR alpha, since it has a low affinity for MTX, we should see a lower amount of that reuptake, right? Or uptake.
For FRA, yeah.
Yeah. So that's just, I haven't looked at the figure yet, but
Alpha.
that
Yeah.
would make sense then, right?
Hmm.
Because of the low affinity. So, um, okay. So uptake rate's less than 0.0125. What's the P here mean?
Pico, right? I'm thinking picomoles.
And what value is that?
10 to the negative 12.
Mhm. Good. Um, so uptake rate's less than this.
Yeah, I don't know, it's something that really confused me. I don't know why they're saying 5 MTHF. I don't know where they got that from.
Oh, isn't that the where was it?
Yeah, say it up here, but it's like,
Oh yeah, the tetrahydrofolate, that thing, right?
yeah, but how does that relate to the MTX, right? Because they said they're taking MTX. I don't think they're the same thing, right? No?
Um, let's see. That over the 106. 106, what can that be?
Oh, wait, no, I think that's just 10 to the 6 cells. Yeah.
Oh, a formatting error then. Uh,
Yeah, there seems to be a lot of that.
that means this many. Um, so okay, I understand. So they said that the 5-MTHF has a low affinity, right?
Yeah.
And they say for the MTX a very low affinity.
Okay. Even worse.
Yes. So that means that whatever the amount that we have of the M 5-MTHF, if it's less than that, right, it's going to be, I believe, something that we should see for the MTX, perhaps.
Mm.
So, but I don't know. But or actually, no, they're saying that if it's less than that, it's statistically insignificant. So maybe not that. But anyway, let's look at the figure here. So we see this figure. We see a y-axis is the amount of moles uh, of that MTHF per million cells. Um, And yeah, if it's a value lower, and I guess we see that here too with like the error bars and stuff. But anyway, so we have the osteo alone with some value here. Oh wait, and then this is extracellular tritium um, labeled thing. Wait a sec. If they're saying that they're measuring at different MTX concentrations, what? They might make this might be a mistake here because UU uptake seems like a couple of mistakes here. But if they're talking about uptake of MTX, but figure one doesn't have anything with MTX.
Yeah, I have no idea what they're doing here.
Yeah, they're saying this uptake was measured at different MTX concentrations, figure one, but we have only uh THF concentrations and stuff here. Well, anyway, it seems like as you have a higher amount of this one goes down. So higher amount of this means lower amount of that. So, okay, whatever. Let's see what else this is saying. You can scroll down to the left. Yeah. The cell growth requirements for different folate cofactors are measured with for each cell line in folate-free media. supplemented with folic acid, 5-MTHF, or lusoverin, a synthetic folic acid analog, as the sole folate source. Okay. Cell number was determined after 72 hours. EC50 is defined as the folate source concentration, producing 50% maximum growth. So we have the LV condition, which is that the lusocorvin thing, synthetic analog.
Yeah, I think so.
Okay. And then FA is the folic acid. Got it. And so for the folic acid, it seems like the osteo on its own goes up. Okay. And then for the MTHF, it goes up even more with a higher amount in osteo. And I suppose that makes sense because these things have, affinities for um,
Folic acid.
the receptor. Um, so, okay. Yeah, it's weird. Okay, so let me see. It has been observed that tumor cells develop resistance to the growth suppressive effect of MTX at a higher frequency than do non-cancerous cells of the same origin. Does the mechanism for MTX resistance proposed in the passage provide a possible explanation for this observation? So, okay. If there's a greater resistance to MTX, so maybe I'll write like, okay, MTX inversely proportional to growth. Um, but in tumor cells, there's a greater resistance to that MTX anti-growth effect, right?
Growth suppressive effect of MTX. Okay. Yeah, I'm with you.
Yeah, meaning a resistance to that. So we know MTX inhibits or suppresses growth, right? But in a tumor cell, that suppression of growth uh, decreases because tumor cells develop a resistance to MTX at a higher frequency than, non-cancerous cells. So we just want to see if the mechanism for the MTX resistance proposed in the passage, if that's an explanation, provides an explanation of that. So,
Okay.
um, immune suppression by cancerous, well, the mechanism here that they talked about
Yeah.
was,
So
what's up?
I mean, for me, when I read that, like the only thing I understood was like MTX just has a low affinity, and they don't really give us much about the graph, right? So,
Uh-huh. Yeah, so I mean, it talks about immune suppression and antibodies, but since they're saying, MTX resistance proposed in the passage, they never mentioned any immune suppression or antibodies, unless I missed it. But
yeah, I don't think so.
yeah, so okay, got it. Now, the mechanism that they hypothesized, I believe, is this that antifolate. Oh, well, that's antifolate resistance. I don't know if MTX. Well, I don't know if MTX is that, but it does say that antifolate resistance comes from the overexpression of FR alpha receptors by cancer cells, right?
Hmm.
Um, okay, let me see. So yes, because MTX blocks a cell's access to folate, which leads to the increased likelihood of cellular modifications that expand the intracellular folate pool. So they're saying researchers in passes hypothesize that overexpression of FR alpha resistance to M. Okay, so that is so I did catch it in the right spot here, right? That it's the overexpression of FR alpha receptors is the mechanism that they propose in the passage, right?
Hmm.
Right over here.
Yeah.
Got it. So, um, okay. Now, if the likelihood of overexpression of FR alpha in rapidly dividing cancer cell populations is increased in response to their heightened metabolic demand for folate, then the likelihood of MTX resistance in that population would be increased. FR alpha receptors appear to provide an alternate means of importing folate sources at a rate greater than that of MTX. Um, so okay, MTX blocks a cell's access to folate, um, which leads to increased likelihood of cellular modifications that expand the intracellular folate pool. Yes, expression of FR alpha by cells that do not ordinarily express it. Okay, I could see why you and a lot of people chose C, but the case is that FR alpha can be expressed normally, but in cancerous cells is overexpressed. C says that cancerous cells express it, but other cells do not express it.
Okay.
So it's not that cancer cells express it and ordinary cells do not express it. It's that ordinary cells express it, the cancer cells overexpress it.
Okay. I see the distinction.
So for this question, STEM, right, they're talking about or they're asking about the mechanism for MTX resistance proposed in the passage, right?
Yeah.
So that means we want to look in the passage for what that mechanism is and
Yeah.
here, right? This
Hmm.
says that so researchers hypothesized, right, that antifolate resistance develops from an overexpression of FR alpha by cancer cells. So cancer cells have an excess of FR alpha receptors. That's why um that's why they can have folate bind to them at a greater rate, and we know folate when it binds causes more DNA replication, right?
Hmm.
So that's why. So if you have more folate receptors, um, and folate causes growth, that's what you're going to see in your cancer cells. So, so C is wrong just because it says do not ordinarily express it.
Okay.
And then D, no FR alpha displays a relatively low affinity for the MTHF, and its action cannot overcome the depleting effect of MTX. So sure, it's a relatively low affinity for that. But um, so its action cannot overcome the depleting effect of MTX. Yeah, I think that let's see the explanation for that because I think it might mention figure one. So it says figure two. Let's see. So relatively no information to support the argument that this uptake cannot occur via FR alpha binding. In fact, given the information in figure two, osteosarcoma cells display 50% maximal growth readily in the presence of any folate source tested, including that. Okay. Which indicates that cells expressing only FR alpha are still able to take a sufficient MTHF at relatively low extracellular concentrations. Um, yeah, I think that, yeah, the way that these are worded could also be kind of tricky. Like B blocks the cell's access to folate, um, which leads to increased likelihood of cellular modifications that expand the intracellular folate pool. Like the solution, like the explanation makes sense, but it's hard to see how that like is being said by saying that it like we know that overexpression of FR alpha, the folate receptor, happens in more so in the tumor cells. And that is what they're saying in the explanation. It's just that the wording of MTX blocks the cell's access to folate, which leads to the increased likelihood of cellular modifications that expand the. All right, maybe they mean this. Maybe they mean this. Maybe they mean that when you have a regular amount of FR alpha, MTX, even though it has a very low affinity for FR alpha, it can
Hmm.
still bind to FR alpha and thereby make it so that some folate can't bind to it. And we know that folate binding to it is what causes that you know, increase in replication. So here it's just saying that if the MTX blocks that access to folate, um, the cellular modification that happens after is to increase the amount of FR alpha folate receptors to cause an increase in the intracellular folate pool, like taking in the folate. So I think that that's what B is saying. I think that the MTX itself blocks the cell's access to folate because it binds to some of the folate receptors, and that the cellular modification happens as a result of that to be like, okay, look, we're not having that much folate being attached to the folate receptor because the MTX is taking up some of that. So
Mm.
let's create more folate receptors.
Okay, that kind of makes sense. Damn, that was
Yeah.
hard.
The wording
Mm.
is like nonsense. It's and
Yeah,
also
because I
this
mean,
also
because
this graph doesn't make sense because they said that they were talking about MTX, but here it's just the MTHF thing. So I don't know what's up with that. But
okay,
yeah, I think this is there might be mistakes here and the wording is pretty pretty bad.
I guess we'll just move on then.
Hmm.
No, not this one. Okay, so this wasn't really a. I don't think so. Yeah, this doesn't really seem like a passage question, but essentially it's just asking for P nitrophenol has a pK of 7.6, whereas ethanol has a pK of 16. What best explains this difference? And I kind of just like I was looking at this point I was like a little bit of a rush because I didn't have much time, but I just picked stability of like it just sounded right, the delocalization of that, and we know that I just realized that's like the conjugation allows the delocalization of the electrons, but is it A or B? I don't know which one it is, but yeah, so yeah, I think NO2 is a electron withdrawing group. Um, yeah, why is C better than B?
Um, NO2, uh,
Donating or withdrawing? I don't know.
um, I think it's electron. Oh, bless you. Um,
Donating? Yeah, it says here it does exhibit a strong electron withdrawing effect. Apparently it's a withdrawing group.
okay, so ethanol, we know what that looks like, right?
Yeah. OH group and two carbons.
And then nitrophenol has a benzene and like I guess
NO2.
H, and then maybe like an NO2.
Yeah.
So let's see. So A and B, so okay. So A is talking about NO2 as an electron donor. B is talking about NO2 as an electron uh withdrawing group. And since we know it's an electron withdrawing group, we can get rid of A. But is that the only thing that we have here? I think the benzene aspect is probably even more important. So B doesn't mention anything about the benzene, so I wouldn't choose that. Um, D says longer carbon backbone. And sure, it's longer, but just because it's longer doesn't mean it's more stable. It's more stable specifically because of resonance. And C says essentially resonance. In other words, like you should know like conjugation is the same thing as resonance, which is the same thing as electron delocalization, which is the same thing as, pi bonds.
Mm.
All these terms mean resonance essentially. So um so that means that uh so for instance, like ethanol, like if it loses its hydrogen, it's just an O minus, and it's not very stable like that. It's not stable at all. Whereas if this one loses its hydrogen to be O minus, it can be like boom, put the electron to make a double bond there, put this one here, and even the NO2 would be something like that, which has resonance itself. So yeah, so it'll be C because you know because we're being asked like what makes it the nitrophenol more acidic, right? And
Yeah.
if something's more acidic, it means that when it loses its proton, it's more stable. So you want to
Okay.
see, okay, the ethanol when it loses its proton, like, is it stable? And the nitrophenol, if it loses its proton, is it stable? And you know that resonance is the main primary thing that causes stability, and that's the main difference between the two. So so yeah, so A is wrong, A is right, but it doesn't best explain the difference because they're asking what best explains this difference. What best explains the difference is the resonance of the benzene. Yeah.
Is Benz like is that a rule that I can follow along and say like the delocalization is typically gonna be one of the more strongest things that cause that help with stability?
Yeah, it's I would say it is the strongest.
The strongest? Okay.
Yeah, like that's how fluorescence works, right? Fluorescence involves a photon of a certain energy getting absorbed, and
Mm-hmm.
that causes an electron to go up to an excited state. And
Mm-hmm.
typically, with when you don't have fluorescence, when the electron goes back to its relaxed state, it emits a photon with the same energy that it absorbed.
Right.
But for fluorescence, let's say it absorbs a photon and it excites an electron. If the molecule has lots of resonance, lots of conjugation, it'll stabilize it. It'll stabilize that excited electron down a step so that when it eventually then goes back to the ground state, it'll emit a photon, but with lower energy because it's dissipated some of that energy through that resonance.
Okay.
Like, what I mean is, like, um, if this energy level is a 1 electron volt and this energy level is 0.5 electron volts, and then this is n is equal to 1, 2, 3, and this is 1.5 electron volts, right? So if you have a regular atom and you shoot a photon that's, let's say, 1.5 electron volts at it, it'll absorb it and it'll excite the electron to this three shell.
Hmm.
But then it'll relax back down, and through conservation of energy, it's going to emit a photon of the same energy of the photon that it absorbed.
So 1.5.
Yep.
Okay.
Now, he's green. If the molecule has a lot of conjugation and it absorbs a 1.5 electron volt photon like this, through its own resonance stabilization, it can relax the electron down to the n is equal to 2 shell without emitting a photon because it loses that energy and gives it to the environment as it stabilizes. So then when the electron does go down to the ground state, it does so from the n is equal to 2 shell rather than the n is equal to 3 shell. So that means that it absorbs a 1.5 electron volt photon, but it emits a 1 electron volt photon.
Okay.
Because what's
Interesting.
happening here is resonance. So fluorescence is a really high yield topic. So you'll see them say things like absorbed a photon at, let's say, 390 nanometers and emitted a photon. Would it be greater than 390 or less than?
Um, Typically it would be, wouldn't it be the same wavelength? Because you're taking the same energy to go to that and you're emitting the same, right?
That would be for this example.
Oh, I guess, okay, well, yeah, I guess in this case it would probably be more, right? Because there's less energy.
Yep. So it'll be like, let's say, like 420 nanometers or something.
Okay.
So, and that's just because like you still have conservation of energy. It's just that at this step here,
Hmm.
you are dissipating energy through resonance stabilization. That's why the molecules that exhibit fluorescence, if you look up what they look like there'll be pigments and dyes, so like melanin, chlorophyll, things like that. If you just look up the structure, it'll have tons and tons of conjugation.
Mm.
So, yeah. So when you think of so like, like this very simple example is like a carboxylic acid, right? It loses its proton, it turns into O minus, and this can go here, this can go here, right?
Hmm.
To give you your O minus and then double bonded O here. So you have resonance here.
Yeah.
Like why is that so like why does this behave as an acid? It behaves as an acid because when it loses its proton, it's more stable because it can have resonance. And
Mm.
acids, and yeah, so that's what we have here. We have a lower pKa for p-nitrophenol, which means it's a stronger acid, which means it's more okay with not with losing a proton.
Yeah, that makes sense. So again, back to this, like what you were saying. So essentially, the resonance allows the molecule to be stabilized and the
Mhm.
release of some of the energy.
Yep.
Thus, when it goes back to the ground state,
Uh-huh.
there's less energy that's being released, basically.
Less energy that's emitted.
Emitted, sorry. Yep, emitted.
Yep. Yep.
Cool. Yeah, I think that was it.
Got it.
Yeah, yeah, I went over these. Okay,
All
cool.
right
Yeah, that
then.
was it.
So I think you're taking a test
Yeah,
this.
I wanted to talk about that. To be honest, it took me a little bit longer to being have to review everything.
Huh?
'Cause it's been a while. Um,
When you
and
say
honestly,
when you
I
say
definitely could have done. Sorry, what you're saying?
when you say it's taking longer to review everything, what do you mean? What are you reviewing?
Like the blueprint, like the full length. Like it took me almost until yesterday to review it. So it took me like 3 days.
3 days, like how
Um,
many hours each day?
Sunday, I mean Sunday it wasn't a lot, like 4 or 5. Um, and then Monday was like it was around the same. And then yesterday was a little bit more. But I finished like
Like
in around the morning.
more than 15 hours?
So it takes honestly, yeah, I would say about 15 to
And,
16
and
hours.
that's for what? Your blind review of your test?
That's including everything, blind review, like going through it and finishing everything.
Tell me more about that. So like when you review your test, like what are you doing exactly?
Okay, I mean, what I've been doing is like I go through the well, I first I don't review it. Like I just go through the blind review first and I do all those questions that I think I got right or wrong.
Wait, so when you do your blind review, which questions are you doing?
Just the question that I got wrong.
Okay.
Like I make a because on Blueprint it shows you little scales. So I'm like, oh, which one's red? So I just make a note of the red ones and then I just
Yeah.
redo it, just the red ones. Um, yeah, so I do that, and then when I finish it, I do my best to like go through it, and if there's a question, if there's like a I don't really understand it, I try to see if it's like a content issue, and then I try to see if I put it in Anki. And I've also made a couple notes too this time, like topics that I struggled with. So like today, this time I struggled with I wanted to review like titrations and gases. So today I was able to kind of like look through gases. So that's kind of the thing that I'm doing. So that's really, yes, that's basically what I'm doing. But again, it's taking me a little bit longer to
Yeah.
review.
I'm trying to see why, because like let's say you have like 15, 20 questions wrong, and then you do your blind review, where you do those 15 to 20 questions without the time constraint. But how long does it take you to do like those 15 to 20 questions blind review?
I didn't really time myself, and that's next time I'm just gonna time myself. I'll put a timer or something. I'd like to say maybe like an hour, maybe
Yeah,
an hour.
'cause it shouldn't take, it shouldn't take that long because to like blind review a section shouldn't take longer than like, yeah, it should take like an hour, hour and a half maybe. So, uh, you know, for like that's like 6 hours, I guess, total for the test, maximum for all the sections. If it's 1.5 hour blind review per section. So yeah, I would, maybe cap it at that. Like, see if you can do your blind review, like for each section, a blind review, like see if you can do it in like an hour, hour and a half max.
Okay.
And yeah, the because yeah, if it takes longer than that, you are better off just, doing that regular review and getting, the answer that way. So yeah, it shouldn't take let's cap it at like maybe like 4 or 5 hours for blind reviewing the entire test.
Like doing the blind review 4 or 5 hours. Like, okay.
Oh, so you're saying the 15 or so hours is the blind review and then the regular review.
Practically. Yeah, I would say that.
So I would say like maybe like yeah, like 3, 4 hours blind review, 2, 3 hours regular review. Regular review should take less time. So uh let's see if we can cut that in half. Like instead of 15 hours, like 7.5 hours for the blind review, the regular review, and all of that stuff.
So should I like that's I guess that's the confusion because like by the time I like when I'm reviewing it, I'm trying to read my answer choices. Like at least honestly, like maybe it takes me like it's like every hour, maybe I go around like I'm just kind of averaging it, maybe like 10 to 15 questions, like reviewing it. So it takes me a while to go through the questions.
Hmm.
Um, so yeah, because like I know how you have your structure, your plan structure, where I would essentially just be doing the review in like one, practically only on Sundays.
Hmm.
If I finish the test on Saturday, I would finish on Sunday. But yeah, just that aspect is like it's just hard for me to see how I can do that in one day.
Yeah, yeah. Yeah, let's okay, so let's do this. Let's have you do it and time yourself. Like not like time yourself like time constraints. Like start at the stopwatch and just see how long it takes you,
Okay.
right? See how long it takes you to, blind review a section, how long it takes you to blind review, the test, how long it takes you to do the regular review of the test. But uh yeah, because it shouldn't be taking that long. So yeah, so let's have you, time yourself again. You know what I mean by that, right?
So I'm just on the side, just put a timer on and see how long it takes me.
Yep, yep. Yeah. So yeah, let's do that. So have you finished blind reviewing the test that you just took?
Yeah, yeah, I finished it all. But the only thing is like now I'm like thinking about it, it's like I mean I have 8, 9, and 10 left,
Mm-hmm.
three of the blueprints, but I still have a little bit of topics. Like I finished the blind review, but like there's topics that I want to practice and do questions on and like um
Yep.
improve those parts like gases or solubility like we went over today.
Yep. Yep.
But if I take the test on Saturday, it's like I
Mhm.
feel like I don't have enough time. So I'm like I don't know if I should move it to next week, taking the 8, because there's only, because blueprint's the best I got right now. So
Your test was that in March or January?
no, it's in March.
Oh, okay. So yeah, so we have time on our side. So yeah, if you want to uh push that test to next weekend, we can do that.
Okay, yeah, I think we should do that.
Yeah. How are the section banks going?
Yeah, I was gonna finish up the chem tonight. So and then I guess next week when we meet, we can just go over the section banks because I see them on Monday. So I think we'll
Yeah,
plan
yeah.
to.
So I guess like yeah, so now you can work on the section bank like uh for like I guess like this week and next week before your test.
Okay.
Let's do that.
Okay. Sounds good. And I just moved to for cars. I've just been doing exam crackers. Like today was my first day, but yeah, that was a weird one.
Uh-huh.
But
Um,
I'll just keep
got it.
doing that. I'm gonna go get my phone real quick. How much is it gonna be?
94.
Okay. Okay. I just sent it to you.
I got it.
Awesome. All right, man. I will see you on Monday.
All right, awesome. Yep, have a good rest of your week and weekend, okay?